Hi there, and welcome back. So now, previous video we studied the standard K-Epsilon. Let's move to the two other variants of the standard K-Epsilon, the K-Epsilon RNG, K-Epsilon Realizable K-Epsilon. Okay, so we move to the deck of slide 3. And well, here we have the description of a few turbulence, a few additional blah. This one we don't have, this is algebraic. So from here you can get an idea also for the Business hypothesis and less models and so on. But in any case, and now here we go. We have the RNG K-Epsilon. So let's talk about this. As usual, here you have the references. Okay, so this is derived from the standard K-Epsilon, the developments here, you have the two references. As usual, Business hypothesis, okay, it's a linear viscosity model. It is based in this renormalization group theory. Very mathematical, I don't follow that very well. Okay, then this model is more reliable than the standard K-Epsilon, for a few applications, okay. Also, it suffers the same deficiencies. That is, it is wall modeling. So the main modification here is that the closure coefficients now they depends. Okay, a few of them depends in the strains there. Okay, so this is in order to reduce the length scales when you have very high strain rates. So in theory, also these models you are going to see that some of the coefficients, but not C mu, you add these functions that are going to change the behavior in function of a quantity or in the distance from the wall. They might improve the results, and also they might give you good results for wall resolving measures, but they are not formulated for that. So do not use this model for wall resolving. Use it for wall modeling, okay? Unless you apply the proper correction to have it in the low reformulation that later we're going to see what is happening there. Okay, so use this model also. The accuracy is improved when you have swirling flows or strain flows. Now you have contraction and expansions and so on. It will improve the accuracy. So these are the equations. As you see, it's pretty much the same. How you compute turbulent viscosity is the same. This is a constant same relationship, but then seeing chance here when you look at this C-Epsilon2, this coefficient here in the dissipation. So look at that. Now you have this dependence, and then you have all these definitions. So as you can see, you add a little bit more complex coefficients on relationship to add a dependence in function of another variable, and you can get an improvement of the model. Your other coefficients, as I mentioned, C mu, and look at that, C mu in this case is 8.85. It's not anymore 8.9. If you want, you can change it, but this is the original formulation. So as I mentioned, wall modeling, okay, but it has been extended to low re using the proper modification. I have to stress that, and here you have the references where they talk about that. What you have in OpenFOAM is high re. Be careful about that. Boundary conditions, they are set exactly the same way that we did for the standard K-Epsilon. Nothing changed, exactly the same way. High. And well, here we have a reference later with B6 to the NASA. Now let's also take a look at the realizable. So between all the three models, this is the one I prefer to use, the realizable K-Epsilon. So same concept as the RNG, let's change something, let's add some dependency, but in this case, okay, by the way, here you have the papers also, the definitions and so the derivation. And the main difference here is that now the coefficient, this one will directly modify C mu, as we saw in the graphics, that it has that dependency when you get closer to the wall. So now C mu is no longer constant, okay? So now you add kind of a blending function, okay, based on some realizability constraints, and you have this dependence and will give you a much better behavior. So also the transport equation for the dissipation rate is a little bit different. There are also there are some differences, but the concept is pretty much the same. This model will give you better results when you have a strong system curvature. In these conditions that you see here, even in adverse pressure gradients, it will give you much better results, separation and recirculation. So basically what is happening here is that it will enforce this condition. So we know by definition the normal Reynolds stresses, they have to be positive. So it's the square. There is no way that they are negative. So basically what they are doing is enforcing this. And they can become negative, but due to modeling. Remember, that we don't have any more exact equations. We are now modeling everything. So it might become negative due to modeling error. So now everything is being enforced. Also, they enforce this inequality. And that's it. So then we go to the governing equation. So we have the K equation that is pretty much similar. Coefficients will be a little bit different, but if you look at the epsilon, this is the main difference here. Okay, but also the eddy viscosity, how we compute it, it is the same way, but now C mu is no longer constant. And here we have the definition. Okay, so this is what is happening. Okay, you add this new function and you are going to regulate using this relationship, how the constancy mu behave as you get different y plus values. Also look at that, we're also adding vorticity. So now an extra component. So in theory it should give better results as we saw previously now for those conditions that you have system rotation and so on. Okay, a little bit more coefficients in mu, so how they're computed, strain rates and so on. As we already say, same limitation as standard K-Epsilon, wall modeling. Here now C mu is variable. Also, as I say, it might give you good result with wall resolving measures, but be careful because in OpenFOAM, the formulation is only wall modeling. So be careful about that. And that's it. Okay, those are the two variants. And just to show you here, we go to the NASA website. And here you have the Chien K-Epsilon. Let's take a look what they show here. So basically they only use here the low re formulation. So governing equations, so on, different functions. And then they talk about boundary condition, and this is the low re, these are your boundary condition. K, the wall is 0, epsilon, the wall is 0. Or the KQ are boundary conditions, okay? So take a look there, and this is it, okay? So look at that also, this specific variation that we have also is computing the distance to the wall, okay? So if we recall, I think we have one of those, the Lien qubit, it compute distance to the wall. So it's not properly the same as we've seen there in the NASA website, but it has that wall distance there, okay? So at this point, we're done with the theory, and let's take a look. So as I mentioned, you have K-Epsilon RNG and K-Epsilon realizable. I'm not going to run. Let's look at the plots. Nothing changed, okay? Absolutely nothing. Boundary conditions. This also, well, obviously you will need to change here the name, okay? But the rest is pretty much the same. Also be careful now, recall that I'm always plotting the production terms. So as you go into control it here, also that is realizable or will be RNG Ka, so get the right production term. But for the rest, it is exactly the same. So just to show you as well, now let me go K-Epsilon realizer. This is the one I like to use, and let me run this one. So as you see, perfect, okay, nothing changed. And let's discuss the results. So we have the high re, and let's take a look at the low re. That we know it is wrong, but it's going to give you a result. So I took the wrong one. Interesting, also take this case and both of the cases and play around with boundary conditions like the wall, K and so on to see the behavior. So look at that as the previous case, the low re pretty much is giving you the wrong results. Okay, as expected, probably a little bit better than the previous case, the standard, but there are wrong results. Same concept here. So look at that now. Here it gets closer to the buffer layer, but still it is in this region where you shouldn't be producing any turbulence. So here we have the peak, also something about an 8, probably is getting better, but it's not properly right. And when we look here, now look at this behavior is very different. So kind of now is under predicting, probably here over predict. It's doing this switching, but this is completely different from the previous one. And here you see the effect of the different mod of the model, no, the different implementation. Also, this might be the case that you need to iterate more. Who knows? So remember, everything here is fixed to 2,000 iterations. Instead, we go here, and everything is perfect. This behavior probably a little bit different from the standard K-Epsilon, but pretty much the same. So nothing to comment there. Now let's go to the RNG and saying, let me open here this one. Okay, we have the results, and let me open the low re here. So saying pretty much the same observations. Okay, low re. Here, look at that, the difference. Now this one, if you compare with the Realizable was kind of trying to get better results, getting closer here, but this one is proper in 2 or 3D when it starts, when you have this intersection. So it's not correct. Also, this is not correct where you have the production. And then if we look here, yeah, over predicting. Okay, so here the behavior is different from the Realizable, but it is completely wrong. If we look here now, this will be the solution for the high re. Everything perfect. Okay, no comment here. So we have RNG, and here we have the Realizable. And for completeness, let me open also the RNG, where the standard K-Epsilon standard, this one here, and let me, will be 3, always in 3, I put that, and this is it. So you compare, so pretty much the standard and the RNG are very similar, okay, but then the Realizable is a little bit different. Okay, this fluctuation there, but pretty much same results. Okay, this is validated. Okay, so here you have the way to validate in the absence now of reference value. Now by looking at this profile, but then you have this reference value, that is the best way, but then you can look at the production, okay, at the budget of shear stresses and so on. So there you go. We studied the 3 variants of the K-Epsilon in OpenFOAM, the standard K-Epsilon. Remember, they are wall modeling. And as you see, it will give you a solution with a word resolving, but it's not the correct solution. Also, let me show you, I like always to plot the residuals. So Python, plot washer. So we can take a look at the residuals and everything perfect. Okay, probably in one point, so K was becoming unbounded, but it's not a big issue. And there you go. So here also, when it comes to the numerics, I'm running the numerics using second order accurate, probably, if I would recall. But you can change it to first order accurate and just take a look at the solution, quantify the errors if there are errors, and make your own conclusions. Okay, but as I said, you can solve the turbulence variables using first order. There is no problems. If you're doing less, yeah, there use high accuracy. Finally here, also when I open here, I looked at, I have a second plot. I don't recall what it was, 1, so 3, 1, okay. Yeah, just assuming, okay. Okay, so that's all for the K-Epsilon family models, the standard one. Then we're going to look at all these variations. So yeah, I hope you're enjoying this series of videos, and see you next time. Bye. By the way, I forgot to cross the models, so let's go here and cross this one. So K-Epsilon, perfect, we covered this model. So another model down. Then Realizable, also covalent, and Realizable. RNG, Realizable. Okay, so now we will focus in the other models. So now this is the true by. See you next time.